Okay, just make sure it's recorded. Okay, so hi everyone. Welcome to attend our Optical Photonic Computing System Optis seminar series. This is supposed to be our 11th seminar. And also, I think that's the first event we have in 2025, right? Last one is still in 2024. So a long time no see. And if you're a new audience, welcome to join this seminar series. Our seminar will be a 1 hour presentation, including 45-minute presentation. And at the end, we'll have 10 to 15 minutes for a Q&A session. So if you haven't registered our mail list, feel free to scan the QR code. And once you register, you can receive all the emails for the incoming events. And also we have a dedicated Slack channel, YouTube channels. So you can also subscribe. So we can also post the videos, right, for you to review and for you to share with your friends. And before that, some logistics. This event, thanks for our speaker, we will record this event later on, right? So our processed version will be shared through our YouTube channel, and also the PDF slides will be online on our official website. So if you want to ask any questions, if it's really quick, probably you can interrupt and ask in the middle, and hopefully that's very short questions. If you have a long question, feel free to type in the Zoom chat box and we will moderate the Q&A sessions at the end, right? The speaker will answer all of them at the end of the talk. So let me generally introduce our speaker today for the 11th seminar, Professor Arka Majumdar. His talk today will be meta-optical encoders for high-resolution real-time computer vision. And Professor Arka Majumdar currently is a professor in electrical computer engineering and physics at the University of Washington. He received his Bachelor in Tech from IIT in 2007, where he was honored with the President's Gold Medal. He completed a Master and PhD in electrical engineering at Stanford University. Also, he spent 1 year at the University of California, Berkeley, and then in the Intel lab as postdoc, right, before he joined UW. Professor Majumdar is also the recipient of many, many awards. You can see multiple Young Investigator Awards from NSF, ONR, OSR, and among others, all different faculty awards, research award. And also, he is the co-founder and technical advisor of Tune Optics, which is a startup commercializing software-defined meta optics. So without further ado, let's welcome Professor Majumdar for the talk, and please take over the floor. Thank you.
Thank you, and I'd like to thank the organizers for inviting me here. Can everyone see my slide and hear me okay?
Yeah, perfect.
Okay, great. Thank you. So I'm going to talk about some of the work that we are doing. Broadly, we can say meta optical encoders for high resolution real time computer vision. It doesn't have to be meta optics; it could be optical as well. But we understand how to do meta optics, so we're going to primarily talk about meta optics. As Jyoti mentioned, that my name is Arka Majumdar. I'm from University of Washington, Seattle. Most of the work that I'm going to present, they are published. Most of them are published results. You can find the paper from my group website, and this is my email if you have any question. I'd like to acknowledge my team and a lot of alumni. You have several collaborators, as I'm going to mention, and different funding agencies who supported different parts of this work. So let's start from very big picture thing, that why we care about photonics for computing, right? I mean, even though we're talking about optical neural network here, but just let's think in broadly why we care for photonics for computing. And the main reason is, light provides an enormous bandwidth. We can do wavelength division multiplexing, but in general, light can support an extremely large amount of bandwidth, and we know that computing requires bandwidth. Communication through optical waveguides can be almost lossless. This is thing that we know from optical fiber optics, that we can get much lower loss compared to metallic interconnects. So that's what one of the makes optics from in general important for information technology. And finally, light does not interact with each other. Okay, so there's an inherent parallelism offered by light. So for example, if you just put, let's say, a display and the camera and lens in between, right? And display has a million pixel, camera has your detector has a million pixel. You essentially create a 10 to the power 12 channel just putting just in one optics, right? So that kind of massive parallelism is very hard to get with electronics. If you two wire that touch each other, that there will be some sort of current going from one wire to another wire. Right. So these are the kind of many reasons why people have historically been interested in looking into optics for computing, or I'm talking about photonics, but in general optics for computing. But optical computing failed. I mean, this is like, if you have don't know, people are like were very much interested back in 1980s. The optical computing did not quite work. And if you look into this optical computing, that why it did not work, and I have talked to many researchers who worked on that field. In fact, my co-advisor worked on optical computing in Stanford for a long time. And based on all this discussion, we can think about there are two different kind of reasons. One is intrinsic reasons. That's basically what's problem with optics. And then there's an extrinsic reasons, which are like, not necessarily optics, but how everything else was going on. So if you think about intrinsic reasons, one of them is that we all know, if you have been to an optics lab, your size is large, you have to align them, and there's a lot of misalignment. So that's the reason optics is generally not very good compared to, like, if you do electronics. Lack of non-linearity. So essentially, light do not interact with each other, which is one of the good thing about light for parallelism, but it's also a bad thing because you cannot have a non-linear interaction between light, right? And if you don't have non-linearity, and this is something that we can go into, we don't have to go to more details, but if you want to make a neural network, you need a non-linearity. Anyone who is saying that you can make a neural network with a linear operation only, that's wrong. You cannot do that. Okay, this is like by proven by so many papers that I think that we don't have to go there, but there's a lack of non-linearity. Finally, lack of tunability. Okay, you cannot really control the optics very easily. Okay, and like you can think about SLM, but they have like the special light modulator is something that people use, but you cannot like run them very fast. So that's the three main reasons why I think optics has some limitations. But there are two more extrinsic reasons in my understanding by talking to the researcher. One is, back in the days, people did not believe neural network works. Okay, and this is actually a kind of fairly important. If you see the history of neural network back in 1980s, when people were looking at neural network, at that time, all support vector machine and many other technology that actually was people thinking is much better for machine learning. The current craze about neural network is only like a 13 years old phenomena. It's not something that was going on for a long time. So people did not quite believe the neural network works, which is no longer true. At least today's day and age, everyone thinks the neural network does something at least. And then the electronic computers and software happens. So electronic becomes much more powerful. And if you know the history of this last 13 years, the reason that neural network people believe it works because it works, and the reason it works because GPU can make them work. But some of the back in the 1980s, this back propagation to train the linear and nonlinear network requires so much computing power, it was just not possible to do, right? But electronic computers became better and better, and optics was like did not really get into that point. So in some way, the optical computing did not really live up to the expectations, and it kind of like went away. But today's day, as I said, the two extrinsic reasons are maybe somewhat alleviated. One is we believe that neural network works. Okay, we need like a very large amount of linear operations, and I'll come back to nonlinearity in a bit, but in a large amount of linear operation, and it turns out that many of the GPUs and you need enormous amount of power to run this vector matrix multiplication. So there is some limitations on the electronics that we keep on hearing, and then there is some skepticism of neural networks. So these extrinsic reasons are somewhat alleviated. What about the intrinsic reasons? So if we look into, like, we are going to talk about meta optics, but there are a lot of work people are doing in integrated photonics. In this new technology, we can actually make a lot of devices on chip. Okay, and we can make like very small lenses, very small optics. You can probably do monolithic integration, so some of the size and misalignment problem is somewhat solved. There's a lot of work on the tunable photonics also, even though I'm not really going to talk much about it. But in general, like, there are many new materials that people are looking into. With integrated photonics, you can confine light in a very small volume that helps you to get better reconfigurability. So that's probably another thing that where people are looking into how do you create like kind of large scale special light modulator, lot of like tune many optical degrees of freedom. So that's another problem that I think people are looking into in much more details, and there are a lot of promising solution. Same thing for emerging materials for nonlinear optics. And that these two are, even though I'm not really going to talk about this to that much in today's talk, but there are a lot of research that's going on, some by my group, but in general, in the overall in the photonics community, there are a lot of new materials that can give you the tunability and nonlinearity, and all those things together. I think this is an important time to revisit this topic of optical computing. So if you look into this optical computing, like photonics computing, there are multiple different ways you can bring optics. So one is optics as interconnect for high performance computing. Now, this is real. This is already being commercialized. So you probably heard that Nvidia talked about silicon photonics. They are doing, but if you were in like in OFC this year, you will see that there are many companies who are trying to build this optical communication in server to support AI. So AI is a very big driver for bringing optics as interconnect for in the server. So to me, that's not technically optics in computing, like, but essentially this part is real. This is already happening. People have thought about digital logic with optics. So can we do binary logic with optics? And in my own opinion, and based on like many people in the community, this is probably not where optics is going to find a very good solution, because electronics are really good at getting binary logic. Okay. uh, Analog computing, and I'm calling it all optical, but this all optical term is poorly understood in my opinion. There's nothing all optical. Okay, there's always an electronics involved. But when we say all optical, what it mean by analog computing all optical is the signal is never explicitly transduced from optics to electronics, but you still need to rely on electrons in some way, because this is still true that light cannot be nonlinear, light cannot interact with each other. There has to be a material platform, there has to be some electrons involved for one light to control another light. So some of this idea that people have looked into this kind of analog computing is kind of more like optoelectronically induced optical nonlinearity, where you take a little bit of the light, you can control, create current, and with that current you can change light transmission, and that's how you can do the nonlinear operation. You can also control the weights. So that, I think, in my opinion, it may make some sense. They are mostly in integrated photonics. There is another approach that many people have talked about, the hybrid electrophotonics computing, where you do linear operation in optics, convert it to electronics, then do nonlinear operation, convert it back to optics, and go back and forth. We have done done several analyses, and we came to the conclusion that this approach has almost no benefit, because this transduction between electronics and optics and electronics is so power hungry and adds so much latency that you never win by this approach. The third one, which is not necessarily and computing, but that is the part that where I am going to focus on today, is if you look into that, where is some of this optical computing being used, right? These are, or some of the neural network being used, not optical computing, in this computer vision, computational imaging, where the information is already in the optical domain. Okay. And there, instead of like trying to get the capture a pristine image and then put it in a AI block, why can't we do some sort of computing or some sort of pre-processing with light? In my opinion, these are the two things where I believe that optical computing and in general can play an important role. This to approach. I am primarily going to focus on the computer vision and not on analog computing, which is mostly an integrated photonics based for, and here is my rationale. And this is a thing that I have struggled for a long time, that we have integrated photonics. And when you say integrated photonics, what I mean by that is light is traveling on chip through waveguide. That's what the integrated photonics is. Free space optics means light is traveling perpendicular to the chip area. So we have used the semiconductor optics, could be meta optics, could be diffractive optics, could be multiple of them. They are changing the light or manipulating the light, as light is propagating perpendicular to the chip, not in the waveguide. Okay. So if we look into this, and there are few parameters that we have thought about. The first, let's think about active functionality, this reconfigurability and nonlinearity. In my opinion, free space optics is very difficult to achieve, because you have very short interaction length in the semiconductor, because whereas in the waveguide you can route light over a longer distance, you can confine light very well, so it's easier to achieve. I want to highlight that it's not easy to achieve, but it's easier than free space optics. The compactness is on chip, like integrated photonics, everything is on chip, so you can make like many devices on chip. Free space optics is generally bulky, but many semiconductor optics, specifically meta optics is what I am going to talk about, but you can also do that with diffractive optics, can help. Um, Alignment tolerance, integrated photonics, everything is aligned, like you're monolithically integrating them, you don't have to like align those optics well. And free space optics had been poorly aligned. You probably, if you're working in optics lab, aligning many optics takes a lot of time. But with the semiconductor meta optics, we are coming to a point where at least there is a possibility of creating like integrating them monolithic way. People actually have done volume optics, not in the uh, short wave infrared or visible, mostly in the mid-wave infrared. But there are some paper recently that came out from Harvard where they actually at least have two meta optics or two layers of meta optics. I know that there are foundries who are actually developing multi-layer meta optics. So it is, you can start making like somewhat better better aligned optics monolithically. It's unlikely to be as good as integrated photonics. So that's the kind of the bad thing about free space optics. But in my opinion, the reason we are going to optics in the first place, okay, is because GPU cannot handle big problem. But the term big is very important. Okay, I say this, and this is, I'm criticizing my work as well. Anyone who does MNIST, handwritten data set, they do it because that's the only thing they can do. It's not by choice. Okay, and MNIST GPU has no problem. MNIST is linearly separable. You can actually do this in a very simple way. Only when GPU has a problem is when your size of your matrix, size of your vector is extremely large. If you think about integrated photonics, your input size scales with boundary. Even with like you can do wavelength division multiplexing, you get another extra factor. But the only way you can get the light in a chip is from the side, from the circumference where you have the gratings. So it scales with L. Whereas free space optics, you can get L square. So this argument that I gave before in the beginning of my talk, that you can put a lens, you can get into the 12 channel, you can get that only because you have this two dimension, that you are essentially using the whole area of the optics to get the light in and out. And finally, the compatibility with the incoherent light. So my argument has been, and I have not been convinced yet, that if the light is not already in the optical domain, is there actually a benefit of optics? So if your light is already in the optical domain, I think there is at least a case to be made for using some sort of optical computing, and they are generally incoherent light. And there are two examples that we have looked into. One is like computer vision, just from like doing like imaging with ambient light. That's all incoherent light, and you cannot really interface them with integrated photonics. There is another work that we have not looked into, but I know that few people are working on in the biological microscopy, because you get this fluorescence particle, fluorescent light coming from your your sample, and then you can probably do some processing, because some of them can be very high throughput, like high throughput computing you need to do to go through many channels. So based on those things, I personally believe that free space optics makes a lot more sense for optical computing. Again, this is my personal opinion. But I do agree that integrated photonics is very good to get this active functionality. And if we want to bring active functionality, that reconfigurability and non-linearity, we somehow have to find the balance between how much we do integrated photonics and free space optics. But today's talk, I'm primarily going to focus on free space optics, and this is something that we are doing for quite some time. That if you have like as a free space optics, maybe a meta optics, and a computational backend, can we co-design that optics with the computational backend to do like any sort of imaging problem, not necessarily only computing? And we have looked into just capturing a very good image. It turns out that meta optics has very bad chromaticity. We can solve that, maybe depth sensing. And then some of the lower problems, like last two challenges, kind of where it's going into kind of more on the computer vision side, that can we actually maybe identify different things, can we do image segmentation, can we understand the whole scene. This is something that we are working on. I'm not really going to talk about it because we don't actually have a very good results on those things. We are working on it, but that's kind of the idea, that where optimizing the optics and computing together, we call it kind of software defined optics. Can we get, like, the best of the both worlds to have high efficiency, low latency, and low energy operation? Okay, as I mentioned that we are working on this for quite some time. So one of the things that we did is full color imaging using single meta optics, and we have, like, actually now experiment done with a 1 centimeter size meta optics, probably the best image quality that anyone has captured with a single meta optics. But having said that, it's still, like, not very good. Like, there are some limitations in terms of imaging what we can do with meta optics. But we have looked into spectroscopy, we can look to varifocal imaging, we have looked into depth sensing. But here we kind of primarily interested in looking into optical computing. And then I believe that what we need to do to get to this kind of optical computing, we have to rethink the deep neural network architecture. I think there is a significant amount of new AI research also has to be done for make the optics more useful for running this kind of neural network kind of application. So let me go on that a little bit. So if you look into any deep neural network, and without going into like a very, very abstract way, essentially you have a bunch of linear, nonlinear operation. Okay. So the linear, then the nonlinear, and that's how you kind of all the network goes, right? And if you look into current deep neural network, it's very deep. So you have many, 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 many layers, but they're also very small. So you don't want like very large, like large systems. One of the reason being, your electronics is not very good at handling very large vector matrix multiplication, and you want to bring nonlinearity very early on to reduce the dimensionality, so your linear operation becomes even less and less. Okay, and the linear layers could be convolutional layer, maybe fully connected layer, locally connected layer. I mean, it depends on what kind of neural network you are using. Nonlinear could be softmax, ReLU, sigmoid, multiple different things. Can we think about bringing lot of linear layers in front, okay, implement that using optics, and then we hand it off to a software or electronics block to do the rest of the nonlinear operation? Okay, so this requires a different kind of architecture altogether than the conventional deep learning architecture. Now, I want to spend some time here because it seems, based on my discussion with many researchers who are working in the optical computing, they feel that the deep learning is something fundamental, that we need to have this depth. Okay, that is not true. So there are actual mathematical theorem that people have proven that if you have an exponentially large linear layer, like one hidden layer exponentially large, and the nonlinearity, you can do the same operation. There is actually very elegant proof by many people, like both mathematical and qualitative proof. So it's not true, there is nothing fundamental about depth, but of course this layer is exponentially large. What I am getting at is, instead of getting this exponentially large, can we find a point where you have still a lot of a big linear operations done in the front, and then you do the nonlinear operation? Because in my opinion, doing this depth with optics is very difficult. You have to go back and forth because nonlinearity is very hard to get in optics. You still want to think them as like, not one layer when you are at least training these networks. Okay, I'll come back to that why that is the case, but for now let's assume that we have these linear layers. It is true you can combine them into one linear layer, of course, because it's all linear operation, but you still want to kind of think them about multiple layers and not one layer. Okay, I'll come back to that when we actually discuss that how we achieve that. Okay, so with that background, I'm going to tell you 3 experiments that we did. We'll start with that photonic advantage of optical encoder. And the idea is to show that can we actually create an optical encoder, right, that has actual and any advantage. Okay, so to do that, our goal was to think about, okay, we were going to use an optics, right? That optics is going to do some sort of operation, okay? and that operation gives me something that is not doesn't look like an image, and I'm going to send it to a backend, right? And we did. So this is so if you think about a purely digital operation for any computer vision, the idea is we use a lens to capture an image. So anytime you're training a network, right, if you think about in real world, that network, that image has to be captured by an optics. Okay, so that optics is a lens. So when you say purely digital, that means I have a lens, it's capturing a scene, and then I'm going to send it to a computational backend. And when you're doing hybrid approach, we have the same computational backend in terms of, like, same number of hyperparameters, so same number of layers, same number of neurons. Of course, their weights will be different, but we have the same hyperparameters, same number of hidden layers. So in that way, we can say that the total energy consumption and latency of the systems are very similar. Okay, this is one of the things that I feel is fairly poorly documented in the literature in optical neural network. One should not compare a problem with GPU performance. Okay, GPU takes a very huge amount of power because GPU is a universal machine. So if you want to really do a benchmark of your optical neural network with an electronic system, you have to do it with an ASIC. And that ASIC can be like extremely low power. I can assure you that for MNIST or even CIFAR 10, even for ImageNet, people can come up with ASIC which will take any power that you are doing lower than that. Okay, so to solve that, what we argued here, we are actually not going to talk about what is the power and latency. We are essentially defining the power and latency by number of operations, and we have the same network. So if you think about here, ambient light, two optics, sensor will have the same number of power, sensor will have like same amount of latency, and in the same network. So power and latency in these two networks are same. And if that is the case, we want to see that when we have higher classification accuracy. Okay, so that's the kind of the framework of the problem. And we are going to train these optics to like extremely like not generic at all. Like this particular optics works for only one application. Okay, and if we do that, that probably is supposed to give you the best performance. Okay, so to do that, what we did is as follows. So for purely digital, we start with some MNIST data set, again because MNIST works. Other things are hard to do. We'll show you some CIFAR 10 results, and we are collecting n number of pixels, and that n number of pixels are going to go to the electronic layer. Okay, and based on the number of operations that you can see, that if I have n pixels, so your sensor requires n pixels, so that power scales with n, and the whole electronic networks power and latency also scales with n. So by controlling the n, if n is very small, my power and latency will take lower power, low value. If n is high, my power and latency will be high. So in one case, I'm just binning the pixel, so that's kind of more like a lens. And the physical system, you can think about, I have a lens, either very crappy lens with a very bad PSF, or I essentially have very few pixels, very large pixel camera. And the other case, we are sending it through a meta optics, which is co-optimized with this backend. And for each amount of pixels, let's say I want to send 1 pixel, I optimize one lens. If I want to send 2 pixels, I want to send another lens. So they are extremely optimized for that particular problem. Okay, so pure digital and hybrid optical digital. And I'll come back that why we did like in some way probably the most useless optics, because it works, does only one thing. Because our goal was that if we don't see advantage in that optics, then how can we say like optics will have advantage in any other case? And I'll come back to some insights that we got from that work. So by controlling the n, I can change the power and latency. So these are the 8 optics that we designed. Okay, so first one is designed that we are getting only 1 pixel, second one is 4, the third was a 9, and so on and so forth. And then we did our experiment, and what we found is extremely interesting in my opinion. Okay, when you send too many number of pixels to our backend, our classification accuracy is same for electronics or ONN plus electronic. And what it means that if my power and latency is not a concern, electronics will always do better than optics. So anyone who is claiming that their optical neural network has high classification accuracy compared to an electronic version of that, there is something wrong in that statement, in my opinion. Okay, and I can tell you that why that is there is something wrong, because one of the main argument of neural network that it is an universal function approximation. So a neural network can model any function. if you give him enough number of parameters. So it can model whatever the optics is doing. Optics has no inherent advantage of doing that operation over an electronic system. Okay, so if power and latency is not a requirement, electronics will always give you higher classification accuracy. And this is what we are seeing here, that if you are sending more and more number of pixels, electronics can classify very well. But we do get an photonic advantage when you send less number of pixels. So essentially, when you have a much lower power and lower latency, at that time, our optical system is going to get better performance than electronic system. However, there is a caveat. The caveat is that classification accuracy where you are getting the photonic advantage, that classification accuracy will be lower than what is possible. And this is very important because let's just think about it. I'm not going to spend too much time on it. You are going to take an autonomous flight and someone told you it has a 5% higher accuracy of having an accident. Will you take that flight or not? Okay, so if we know that our AI will be acting slightly worse but with a much lower power and latency, what are the applications where actually this will be useful? I don't know, but I doubt this will be like for something that is extremely sensitive and human life is at risk. Okay, so this is kind of one of the things that I was saying, like it's kind of very extremely optimized, and even there we did see an photonic advantage, but it happens at a regime where the overall classification accuracy is lower. Okay, so let's do something that's a little bit more useful. Okay, and I'm not going to go into too much details on the especially varying property, but the idea was that can we do any generic convolution? So in incoherent light, if this is my object and this is my incoherent PSF, just by sending the object through the optics with a some point state function, I can get a convolution done when you get the captured image. And this is some of the more details in object density, image density. So I can actually design an optics that has some specific point state function. And if I get that point state function just by passing light through that optics, I can get a convolution operation done. So that's the idea. There are some trick to it. The convolutional kernel that we are doing is an incoherent PSF, so it's all positive, right? So, but any neural network kernel has both positive and negative. So we break it down to positive part and negative part, and then you do digital subtraction. So you just take the two image and you subtract it. I like to point out here, which is quite not surprising, that this kind of approach is not new. People have tried this. It's called dual pupil synthesis back in 1980s, and people are like, in my experience, like people that who worked in 1970s and 80s, they were extremely smart and they thought about a lot of new ideas, which I think yeah, we should go back and read those papers more carefully. But it did not work, and one of the reasons they did not work because they wanted to match the convolution. I and the reason what happens is when you're digitally subtracting it, the noise doesn't get subtracted. Noise actually get added, and that's what makes a very big problem. But we have a computational backend, so we are not relying purely on optics. We have an optical front end, and that's what we call encoder. But then you have a computational backend, and we can make the backend more robust against excess noise, which is something that we can do with our current lot of training method. It's not just like this is like the huge amount of literature on that. So we actually use that, and then we kind of pose this as a point state function problem. And I just want to kind of talk a little bit about it. So this is the PSF that we get, like from this is the kernel that we get from our convolution. We use that as a pose as a holography problem, that design an optics that give me this as my point state function, and we get something that looks like this. It's not exactly same. There are some challenges, like if there is no guarantee that an optics can be found with the desired PSF, so, but we want to go something that is close. So for example, like if you look into it, you can say there is a diagonal, you can see a diagonal here. Okay, there's a bright spot, there is a bright spot here. So something that close to it, and then we can implement all of them like in an array of optics. So basically you can think about array of those optics. We have image, incoherent light, all of them we are going to create some individual image, then we can do digital subtraction and the computational backend. Okay, this is how it looks like. So this is actually extremely simple setup. We just replace the lens with this array of meta surface. We capture all the images and then it goes to the backend. Okay, this is how each of the meta optics looks like. So they have this PSF that we are talking about. So in this particular case, we did around, I think, 45 small meta optics. So each of them is going, or not 46, because for each one of them we have two, positive and negative. I'm going to, like, we're running, I'm going to skip these results, and this is what we get. Okay, that with the purely electronic, we need 57 million parameters and 72.64% accuracy. With hybrid optical digital, we get only 2000 parameters and 73.8% accuracy. Two things here. One, these accuracies are way lower than state of the art electronic network. If you have, like, more than 57 million parameters, like a billion parameters, you can go like 90% accuracy. This is done with the cipher 10, which is consistent with the fact that we are getting some photonic advantage in terms of, like, number of parameters that we need to train, but at lower classification accuracy. The other thing that I want to, like, point out, that we did get a slightly higher classification accuracy compared to purely electronic, which should not have happened, okay, based on the argument that I gave you just now in the previous slide. The reason it happening is because, and that's why we call it spatially varying optics, because when you saying that the PSF, like, we're assuming a convolution, and that convolution essentially means that my convolution kernel is same throughout the image, okay, but and that's how we model our digital system. But our pure in a pure hybrid optical digital system, when you're actually using real optics, your PSF is not same. PSF is spatially varying. That means that you are not doing actually a pure convolution, you are doing a locally connected layer, and it turns out that locally connected layer is supposed to give you better classification accuracy. So if you did the locally connected layer in the purely electronic system, which will again increase the number of parameters significantly, we will get more than 73.8% accuracy. Okay, so that's why we get a slightly higher accuracy than the electronic system. Okay, so last part, the compressed meta-optical interconnect. So why multiple layers? Okay, I told you because. So one of the problem with this kind of, designing just one optics and end-to-end design is your optics become very large. So often you want to kind of still model it as an electronic neural network. You get all the convolution and then somehow collapse it to a small convolution. But if you start modeling them as a single optics, right, it has way more design degree of freedom. And if you don't believe me, just think about it. Write a convolution operation as a matrix operation. Okay, so convolution has maybe 9 independent elements, but when you write it in a matrix, it's a humongous matrix. And how do you know which one's a training parameter, which one is not? So if you just collapse them in a single layer, you get a huge number of training parameters, which is hard to kind of keep track of. So you're still better off thinking that these are separate operation, okay, so that you know that you don't have that many training not many training parameters, and then once you have those, you can collapse them to one linear layer that you can implement with the optics. Okay, so there's a little bit trick to it, and I'll be happy to kind of discuss more, but you do not really want to think about a single layer. There are a lot of challenges with that. So, but even if you have all those layers, there was nonlinearity before. How do you remove it? So there is a technique. Again, this is not done by us. It's called knowledge distillation. It's actually pioneered by Jeffrey Hinton, and they use it in Google and many other places to prune the network. So network has a lot of extra, connections. So you can remove that to reduce the power. But we use this knowledge distillation technique, and I'm not going to go into too much details, but it has a teacher and student network, and we create two error. One is a hard error that is like, the basically saying, I mean, one way to think about it, 3 and 8 are kind of similar. Okay, so if you call 3 as a 8, you would pay, your teacher pay less penalty to you. But if you call 3 as a 1, that's probably like you really don't know what you are doing, right? So you put another soft error. uh, with that, we train a much more simpler network without any nonlinearity. And then, so we start with this AlexNet. We have a 5 convolutional layer with, all the nonlinearity. We use knowledge distillation to collapse them to a single convolutional layer, and we take this convolutional layer and then we implement with a single meta optics, exactly like the way I did it before. And this is how the kind of optics looks like, and this is done with the MNIST. This is the structure here. I'm not going to go more details, but this is the result that we get. So if you have like purely electronic software, we get like around like 98.9% accuracy. With our hybrid approach, we did get a 5% reduction, which is consistent with our initial finding, But we did get a significant reduction in the MAC operation, which is one of the things that we are saying that you can get this reduced latency and energy. Now, one of the things that meta optics can give me three different PSA for three different colors. So if you're working on a colored imaging, right, RGB, I can get three. If you look into like CIFAR 10 or ImageNet, people always do 3 channel with a different convolution. I can just do that implementing different PSF in different color. So that's what we did. So in this case, we have one meta optics that gives us three different point state function or three different kernel for three different color. And with this, what we got is again fairly consistent. We get a reduction in the accuracy, but we get a significant, almost 4 orders of magnitude reduction. In the operation, as you see here, that this is the number of MAC operations that we need in electronic system. Hybrid optoelectronic, we need only 150,000. So we do see a reduction in energy and latency, but it comes with a reduction in operation, a reduction in accuracy. So there's another thing that we did. We essentially did something called transfer learning. So we have this optics, which is static optics. We cannot change it, but can we change just the back end? So we have this compressed CNN that we have the front end remains same, but we just change the back end. And with that, we basically took it to a completely different data set. In this case, is something called high 10, and we get like still like more than what you expect from just pure random operation. So my whole point is that this optics that we designed with our convolution for image for CIFAR 10 is actually capturing some of these features, which is probably a little bit more generic, so we can use it for another data set altogether. So do we improve on energy per frame? And that's the part that I think is important to ask, that ultimately there's energy benefit. And this is also important to recognize. So we have two data sets we have done, MNIST digital and MNIST hybrid ONN. So this is important, that if you look into just the compute energy, and often people just talk about this compute energy, you see a significant improvement in all these cases. Micro to nanojoule, it seems like orders and orders of magnitude improvement. But there is a sensor energy which we cannot neglect. So if you are doing these convolutions, you are actually have to capture many large number of pixels. So with those two things, we still get some high amount of some improvement, but it's not like many orders of magnitude. And we have looked into a survey, and we found that many paper have neglected camera or laser power to quote a extremely large improvement, but that improvement is not real because you have to do like whole wall plug efficiency. One of the things that we also find that the CIFAR 10 actually you get a higher performance improvement compared to MNIST. So that's another insight that I think we are trying to kind of validate more, that more complex scenes where high resolution is absolutely necessary when and may provide some advantage. So in this argument, I want to say like some of the argument that optics people give, that I have an MNIST data set, and the MNIST image I can put a million pixel MNIST image and we'll get some benefit. But why you want to do that, right? You don't need a million pixel for an MNIST image. Even 8 by 8 is good enough. But if you think about a realistic scene, and one of the things that I talk about, like a small plane in a big blue sky, you really need high resolution image. And that's where some of this optical encoder might be more useful than this curated data set that we are working with. And we want to go there, and that's something that we are working on right now. I'm going to spend very quickly that instead of neural network, another thing that I feel that might be interesting to look into is mathematical transformation, because these are data set independent. So one of the things that we did recently is radon transform, and we show that it works. But one of the things that's interesting here, that when you do this radon transform, okay, and I have an image where we have we put this MNIST in the diagonal, we just created an actual image, and then we compressed it with average pooling. Average pooling essentially like a binning or radon reconstruction. What we find that radon actually works better than like just kind of binning the pixel. Okay, basically the insight here, without going into more details, that when most of the pixels in an image does not have any information, or you have a very sparse image, maybe there you can get some benefit from optics. Okay, so for example, if you have a MNIST data set, actually most of the pixels are very useful for you to tell you that what that image is. So I can actually start binning them and I still get all the information. But if you have a very sparse scene, let's think about like a big screen with a small one here. If you start binning, you are going to completely lose the one. So, so photonic advantage may be achieved in more realistic scene. So I think I'm kind of coming to a close. I'm going to say like, the synergy of photonics and computation. I think it can open up new opportunity. I think there's two insight that I believe that photonic advantage can be achieved when you reduce your power and latency significantly, but it will come again. I cannot say like with certainty, but based on our experiment and somewhat like qualitative argument that our classification accuracy will be lower, and it is possible that optics might be more beneficial for complex scene. I'm going to skip these things, but I want to kind of spend one slide here just like conclude that I believe, I mean, this is my take on optical information processing, and I call it game of computing. Okay, the thing is that if you go to any conference, right, people talks about like new material, new devices, new architecture. What they're trying to make is best optical computer. Okay, but that's not our competition, right? We have to deal with electronics. Okay, and if you have not watched Game of Thrones, you'll probably not understand this slide, and my apologies for that. But you have to be better than electronics, and it's not just electronics. Electronics comes with software. That's the thing that you need to beat. Like, goal is never to build the best optical computer, but rather to build one that is superior than electrical implementation. Okay, and I feel that it is unlikely that optical computing will be good for a generic purpose machine. We really need to find a niche application from ONN, and my bet is if the light is already in the optical domain and free space is where you find the main application. And I'm almost certain that whatever we do, like the things that ultimately like where the ONN is going to be used, probably no one can figure out that what that is. Yeah. So thank you, and I'll be happy to take any question.
Great. Yeah, thanks for the great talk. We do have quite some questions here. Let me went through them. Okay, the first question says in the slides that titled classification accuracy, why there is accuracy drop between the hybrid system and the experiment results at the left side of the curve.
So which slide? I mean, you mean this one or?
Uh, maybe there's a graph, right, showing the accuracy curve, compare three curves. Yeah,
Oh, you mean
maybe,
this one?
yeah.
I guess this one is talking about. Yeah, so that's just coming from the experimental accuracy because we have more noise. I think that's why that. So I mean, it's probably not surprising that experiment gives better worse result because the noise we added some noise, but in experiment this is the real noise that we are getting. So that's why you think at the low pixel we get a much higher noise. Yeah.
Okay, yeah. Maybe a follow-up question. I can group the questions, right? Another question also ask the robustness. So, how robust are those hybrid optical digital systems? If it relies on digital backend to tolerate the noise, how about for any other applications besides AI, like scientific computing, which requires really high precision?
I do not think that for scientific computing these things are very good. That's my own opinion. Like, bit resolution is not very large. This is really good for like computer vision application, but for scientific computing, I am not convinced that we have the bit resolution to give very good accuracy. I want to point out one thing that we did here. So our back, so we of course we train everything in software first. We have a then we design the optics. We have a back end, but when you do experiment, we don't change the backend. Backend remains same, but experiment has a lot of non-idealities. So what to solve that, we essentially just add an additional calibration layer, which are in our paper, and we just train only the calibration layer. So backend is fixed, optics is fixed. We just train only that only the fully connected calibration layer to get the results that we get. Without that, the experimental noise and added imperfection doesn't quite work. But scientific computing, I personally am not convinced that this is the way to go for scientific computing.
Okay, yeah, I think also partially answers the next question. That means, will this meta-optic system have the capability to mimic arbitrary convolution kernels for a
Yes,
specific requirement?
I think that you can do arbitrary convolutional kernel in the sense that as long as you get close enough. But there
Mhm.
is another thing that we are doing. I did not arbitrary vector matrix multiplication. So if you have three layers of optics, you can do any arbitrary vector matrix multiplication with a very large, like almost like 10 to the power 17 operations that you can do, like at least, in the meta optics scale. But this cannot be, I don't think it can be done with a single optics. But we have done fairly complex convolution for CFERT-net. We have some results right now on ImageNet and UNet where we can also do those things. So I think you can do fairly complex convolution. Right now, our convolution kernel, I think, is size is 16 by 16. These are bigger than what you generally do because we are collapsing them, so it gets bigger. But at some point of time, I do agree that if your convolution size becomes too large, then your signal to noise ratio becomes a problem because your PSF becomes too large. So then it doesn't work.
I see. I see. Even though probably in machine learning, they promote a super large kernel, right? Convolution. Probably from physics point of view, you just spread energy to
That's correct. So I think when you're doing optically, you are spreading energy. So I don't know that number. I know
Mm,
that there will be at some point of time, if the PSF is too big,
mm,
then your signal to noise ratio is going to kill you.
mm. Yeah, very good point. Next question is actually asked by me, right? So regarding the comparison between the PIC, and free space, one of the claim is like PIC IO is only on the edge, right? Edge coupler, so it's linear to the size. Recently also a trend, right? Look at multiple chiplets, wafer scale, even panel scale, large integrated system with even 3D photonic VS. Well, those large scale 3D integration, partially solve the problem with, limited IO for PIC.
So, okay, if you are getting light out here, to me, that's free space. Okay.
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 So I did not talk too much about it. So I think that ultimately we need both integrated photonics and free space because all the things that I told you about is completely static, no tuning, no nonlinearity. If you don't have reconfigurability and nonlinearity, I do not see that this is going to be very useful. But
Mm,
bringing nonlinear and tunability, somehow you need to do integrated photonics and free space. And in one of the things that where I feel that academics can make a very big impact, that how efficiently we couple light from integrated to free space. Because all those things, the VIA and everything, my understanding is they are fairly lossy. But
mm,
I do agree that there has to be a new architecture that requires both integrated and meta optics.
mhm. Yeah, yeah. Sometimes the light is actually confined in a vertical via, right? They're trying to use a high index, hollow fiber to confine it. Recently DARPA is trying to promote like
Yeah,
deep.
so maybe like we should not call it free space, but
Okay.
basically my whole point is that this integrated photonics is like, the ordinary vector matrix multiplication. There's a lot of papers. To me, I don't quite see how it will scale, even with
Mhm.
WDM.
Even with WDM mode division. Okay.
Yeah, the wavelength division, yes, you get maybe a factor of 20, factor of 30, but the L squared, that gives you a significant amount. Now, I will say, and this is something that I am very interested in understanding. If you think about our current brain, again, none of these things are like brain, but brain has a 3D connectivity. How do you get 3D connectivity is a very important problem. And in my understanding, there has to be some sort of wave like effect. Otherwise, how can we connect like multiple layers? So that's kind of one of the things for optics. But then you 3D, all those things also has to be controlled in some way.
Yeah, yeah, yeah.
Yeah, and yeah.
Hopefully better technology can be proposed later, right, to enable this, 3D connections. Another question from like Nathan is like, it's great to have data already in the optical domain. How about any intermediate results if you have a multi-layer neural network with activation in between? Otherwise, you need the optical memory.
Okay, so I don't know exactly what you mean, but I think ultimately a single like even if we collapse many of them into single convolution,
Mm,
it still may not be good enough. You might need some nonlinearity and multiple optics. And in my opinion, this is not my work. The only thing that I felt is actually makes sense is what Peter did, Peter McMahon, and we went to grad school together in nature photonics with image intensifier, because not only it does nonlinearity, it does signal regeneration. So a lot of people are doing nonlinearity, but if your signal strength goes down after nonlinearity, you ultimately going to get hit in the signal noise ratio. So not only you need nonlinear activation, you need signal regeneration, and that's the only paper I know which does that. So I actually think this is probably the most promising route to get the nonlinearity. Even for like integrated photonics, even if you do like integrated photonics, people have another laser that basically pump the other one, but somehow you have to get back the signal to the high level.
Some kind of repeater, right? It's missing early photon.
Exactly. You need a repeater somewhere. If you don't have a repeater, I don't see how do you kind of, cascade it. And this is actually, I actually really like this paper. Again,
Mm.
it's not my paper, it's Peter's paper. But it does the active nonlinear activation and regeneration at the same time.
Oh, yeah, very good point. Next question. Thank you for the wonderful talk from Yu Tian. May I just ask a practical question about training DNN based on matte optics? Because fabricating lenses and testing can be quite long round. Would you use a digital twin for training and identifying best shape of girdles before move to really fabrication?
So, I mean, okay, this is, there are two answers to it. We already are doing it. Like we are basically training these things, and we have a very good model for meta optics that kind of works. But the thing is that it's not good enough. And this basically, there are a lot of work people are doing on multi-scale electromagnetic modeling, that how do you model very large area meta lens. That's a very active area of research. Many people are working on. Stephen Johnson has a lot of paper, even Shanui has paper, Flex Computing is doing it. Um, in my opinion, is there are a lot of people are looking into like parts of it, like people are looking into more computing to get this meta optics design and maybe AI training. But I think the what is missing right now, in my opinion, is a kind of a system level understanding that where these things are going. And I was in OFC and I was very impressed by amount of progress people have done in integrated photonics and the foundry level. But if communication is the only thing optics can do, I mean, that's like only one device or few devices. I don't see a growing market, and someone has to solve this problem. But as for the digital twin, I think there is a lot of interest in creating a very good model for meta optics. I believe we already have something that kind of works. But if you have a better model that can run like, a reasonable time, I think many people will be very interested.
Yeah. Typically for digital twin, right, we also implies probably have a closed loop using AI also for those system design. So probably this optical AI can also, have a closed loop.
Maybe. I mean, there are some work that people have done, like, the optical system for solving electromagnetics, a
Mm.
Maxwell's equation. Could be interesting, right? But I don't know. I mean, that's something that we are also doing a lot of work on the large area meta optics design, and we have a lot of collaborators that we are working with. Uh, but many of those techniques are too complex to implement. So this is actually our approach is very simple. Simple. It's essentially what we do. It I did not discuss that much. We have the meta atom. We map. We have a interpolative function between a differentiable function between meta atoms and the phase, and then we have wave optics. Okay, it's actually fairly inaccurate model, but it kind of works.
Okay, so this model is accurate enough to support the real testing.
Exactly. But then the question that becomes that we don't know the answer. That how, I mean, it works for cipher 10. It works
Mm.
for MNIST. It kind of works for also like image segmentation. But when does it fail, right? But this is the one of the thing that if you look into current AI is no longer a theoretical field. It's a very empirical field. They try it and see what works, and that works. And I think that's kind of our approach has been in this kind of large area meta optics. Let's do some approximation and see if it works or not. If it doesn't work, then we can go more complex model.
Okay, let me check if there are any other questions. Probably, I know this talk, it didn't touch a lot on the reconfigurability side, right? So I do like wondering how to ultimately solve the, tunability, make these things reconfigurable, like EO conversion base or any other.
So I have written some paper. There's an opinion article, and I did not get time to do that. So
Mhm.
we are working on some work on the phase change material. I don't quite know whether that is the best way to do it,
Mhm.
but if you look into that, how do you solve many degrees of many pixels at the same time? Okay, this is not an optics problem. This is an electronics problem, in my opinion. Okay, and instead, if you just try drawing this current, this is like in this opinion article we talked about it. So you need to have this electrical wire, you need to have the photonic wire, and they will start touching. Okay, so argument here, and this is the part that I was telling you about. So our approach, and this is something that we are currently working on, that we have this integrated photonic systems which all fed by the same laser, and then we have a backplane that comes in and control each of this element, and we pick up the light from grating next to this one, and then but if you do this kind of approach, your pixels are very far apart, you get a lot of higher order diffraction. So instead of losing light there, we are putting a meta optics just next to these gratings to give, like, combine those beams to an ordered array, like a sub wavelength based. I'm not going to, again, this is an opinion article that we wrote about this. The idea is you use integrated photonics to get the energy efficiency for tuning. You pick up the light just on the ring, not with the, with the waveguide. So that's why I'm saying it has to go to free space. But if you let this light go to free space, the light is going to interact and you're going to get, like, lot of spot. But I can pick up the light very close to near field, give enough k vector to create an ordered array. Another thing that I just saw in the OFC, which I found it to be very interesting, people can do, like, this fiber thing. So you can think about, like, you are putting some fiber and 3D fiber and bringing these fibers close by to create this kind of array. Of course, this is like a more fancy technology, but it seems like people are looking into some of this 3D printed fiber for, free space fiber to meta integrated photonics connection. I think that's another very promising direction to go. Which So that's kind of one of the reconfigurable stuff. And in this case, you know my whole argument is we don't need very high speed. We can do maybe even PN, like, because I can get still like 100 megahertz, but I have so many pixels, so I can get very high bandwidth that way.
Yeah, yeah, it's true. We don't really need 10 gigahertz programming for those meta surveys. You just need
No, so I think the one of the main thing that, I mean, I didn't have time to go over the active functionality. If you really rely on the parallel processing of light, each nonlinearity and each reconfigurability doesn't have to be ultra fast. And when you go to that regime where the nonlinearity is not very fast, then nonlinearity can be very slow. Okay, so it can be very strong. So slow nonlinearity is also strong. So there's a very nice paper by Jacob Kurgin in Nature Photonics. He talks about the slow nonlinearity is always strong, and he kind of say, like, you need fast nonlinearity. But my argument is, if you are having all this beam coming together, you can actually deal with slow nonlinearity as long as it's very strong, and we can do that with, like, ambient light. And if you think about, like, some of the self electro-optic device that David Miller has looked into, and highly encourage, like, new generation people go back in 60s and 70s and 80s, they have a lot of new ideas that people forgot. So we should read those things to understand that, where the, yeah, there are a lot of new ideas there.
I think that's a very great suggestion. Students, I know there are a lot of students attendees here, so get some like really good education suggestions here. Okay. Okay, things time is up. Thanks very much for the great talk and very detailed technical discussion. And also thanks everyone for joining our 11th seminar. It's a very in-depth perspective on optical computing. Also, our audience asked where is the video recording, right? So later on, we will prepare the video and upload to our YouTube channel. So feel free to review that and share that with your friends. Okay, and also later on, we can upload the PDF version of the slides. Okay, thanks. I think this concludes today's events. Thanks very much. Thanks again. Yeah, very nice to have you today.
Okay, that's good. And I'll send you the slide. Okay.
Okay, perfect,
Thank you.
perfect.
Thank
Okay.
you. Thank
Okay.
you.
Thanks. Bye.